Okay, so let me begin by thanking the organizers for uh, creating this very nice workshop. I have really enjoyed all the talks here. It's unfortunate that I couldn't attend this meeting physically because of some personal constraints, but nonetheless, I'm following almost all the talks online. So, so in this talk, I'll also discuss a bit of the physics of the quantum dynamo model as well as the quantum link model, which is closely related to the dynamo model. But unlike the previous two talks, I'll focus more on the high energy properties of these two very paradigmatic models. So hopefully you'll enjoy sort of the new thing that we have discovered here. Okay, so right. So before I begin with the physics proper here, let me acknowledge my collaborators. So essentially, I'll discuss these two papers here. And there's some related work also done in this last paper, but probably I won't get the time to get on to this. So Saptarshi Biswas was a sort of a undergraduate student in IISER Kolkata, and Devashish Banerjee is a colleague of mine in a neighboring institute, Shaha Institute in Kolkata. And after finishing this work, Saptarshi has moved on to US to sort of continue in physics and do his PhD there. Okay. So as I said, I'll basically focus on the high energy aspects of certain paradigmatic quantum dynamo models. And basically, the central theme here is to understand the thermalization of macroscopic systems. So one of the classic things that we encounter in our everyday life is, suppose I start a system with a non-equilibrium state, and I just let it go, and the system is macroscopic and sufficiently complicated, then it reaches a unique equilibrium state when left on its own. Okay, and if you start with different initial conditions, the memory of most of the aspects of the initial condition is lost as it sort of reaches equilibrium. Okay, so now we raise the question that whether macroscopic quantum systems can self-thermalize. Okay, so that's the question being asked in this talk. So the setting is the following. So let's consider any lattice system, let's say your favorite spin system or something with a short-ranged local Hamiltonian. And let's say I prepare the system in some wave function psi naught. And this wave function is something which can be, which is, let's say, an unentangled state or a state with a small entanglement, which can be prepared easily in a laboratory setting. And then one lets the system propagate according to the Hamiltonian. Okay, so it's a purely unitary evolution like this. And then we ask, can the system self-thermalize? Now, this question seems to make no sense because we know from quantum mechanics that unitary evolution cannot erase quantum information. But the point here is we would like to only focus on local operators or local correlation functions. And then it turns out that there's a very interesting dynamics of quantum entanglement as a function of time. And what happens is that this memory of the initial state keeps on progressively moving to more and more non-local operators in space. And if you wait long enough and you only measure sort of the state at some long time with local probes, then most of the memory of the initial state is lost. And that again sounds like thermalization, right? And a key sort of technical result here is basically there's something called eigenstate thermalization hypothesis, which is a super universal result, which basically states that many body eigenstates of local Hamiltonians with a finite energy density appear thermal if one looks at local operators. And the temperature is basically set by this finite energy density. Okay. So now the question that we raise here is that this sort of almost super universal sounding paradigm of self-thermalization in a complicated quantum system, can this be evaded in a disorder-free system? Now, I stress this phrase disorder-free because it turns out that there is a way of evading this thermalization by something called many-body localization, which is an interesting interacting version of the Anderson localization phenomenon. Okay, so but here we focus on disorder-free systems, and we ask, can such systems also, can there be systems which have no disorder but nonetheless evade this paradigm of self-thermalization through unitary evolution? And it turns out that the answer is yes. And this is a very active field of research, and a lot of progress has been made in this for, let's say, the last 5 years or so. And in this talk, I would actually focus on two paradigmatic models of quantum magnetism, the quantum dynamo model as well as the quantum link model. And my task has been made much easier due to the previous lectures by Kedar and Srijit. Okay, so even though I'll focus on two very specific models here, I would like to sort of give a general bird's eye view of the physics that's happening here. At least I believe that's what's happening here. So consider some Hamiltonian which has some tuning parameter lambda here, and let's say there is some operator T and there is some operator O, and as is usual for most interesting quantum problems, let's say this T does not commute with O. Okay, then for the class of models that I'm considering, suppose you tune this lambda to 0, then in this parameter space, there are these special points which I call mother points, where due to a particular index theorem, there is a null space which is protected by this index theorem, and it's not at all hard to sort of think of paradigmatic models which have these kinds of special points. And then if one adds suitable perturbations which break this index theorem, then in these strongly correlated models, one actually has a very good chance of seeing anomalous thermalization. Okay, so that's the main punchline that I'm trying to drive home, and I'll take two particular examples in this talk. Okay, so the examples are the quantum link and the quantum dynamo model. So basically, the quantum dynamo model was already introduced. So these are your dimers. And the quantum link model is basically closely related. So you think of fluxes. So most of us have sort of encountered spin-ice physics when studying frustrated magnets one way or the other. So you see there are these 2-in, 2-out rules. So these fluxes also satisfy the 2-in, 2-out rule. And for simplicity, I just take these systems on ladders. Okay, and then in the quantum link model, basically at each point, the fluxes exactly cancel out. So if 2 arrows come in, 2 arrows also go out. Whereas in the quantum dynamo model, at these red sides, 3 flux lines go out, whereas 1 goes in, and exactly the opposite happens on these blue open circles. Okay, and you can think of these objects as dimers, right? So basically, the only difference between this problem and this problem is these local constraints. Okay, and then as was already introduced, this is a highly constrained model. And then we can imagine putting some local quantum dynamics in this model. So the simplest local quantum dynamics that one can imagine is, let's say I take an elementary plaquette here, and let's say the circulation of fluxes is clockwise or anti-clockwise. And then there is a kinetic operator, which I call Okin, which just flips this circulation from clockwise to anti-clockwise and vice versa. And if it finds something which is neither clockwise nor anti-clockwise, it just annihilates it. So that's the simplest quantum dynamics, which maintains the constraints of this Hilbert space. Also, to sort of make this problem more interesting, we can imagine putting a potential term, okay, which is sort of diagonal in this flux basis, which simply counts the number of these flippable plaquettes, as I have illustrated here. So this is a diagonal term, whereas this is an off-diagonal term. Okay, good. And this is the well-known RK Hamiltonian, Rokshar-Kivelson Hamiltonian, which has already been introduced. So there is this kinetic term here, which sort of flips the fluxes. And there is this potential term here, which just counts the number of elementary plaquettes which have either clockwise circulation of these fluxes or anti-clockwise circulation. And there's this tuning parameter lambda. Okay. And of course, by tuning lambda, one can drive home interesting phase transitions. And acts as interesting phases in such models. For example, if you take this model in 3 dimensions, in particular on the diamond lattice, which is the dual to the pyrochlore lattice, then it's sort of well known now that as you tune in lambda, there are ordered phases, but there's also a very interesting disordered phase, which is basically a U1 quantum spin liquid. And in fact, some of the participants of this workshop have done very interesting work in this particular model and also the closely related XXZ model on the pyrochlore lattice. Okay, so yeah. So basically what I'm going to illustrate here is that there is a very interesting order by disorder mechanism in Hilbert space here, which actually leads to anomalous thermalization for this class of models. So let's take the Rokshar-Kivelson Hamiltonian, and in particular, let's take lambda equal to 0. Okay. So when I take lambda equal to 0, as I'll show here, there is a particular index theorem, which even though the system is a highly interacting theory, nonetheless ensures that there is a macroscopic number of exact zero modes in the spectrum of this theory. Okay. Now, when one turns on a finite lambda in this theory, this index theorem is violated. Because this index theorem is violated, I would expect that these zero modes hybridize with the non-zero modes to form new excitations or new many-body eigenstates of this theory. But what happens remarkably is that certain special zero modes, which I indicate by these red arrows, they simultaneously diagonalize the kinetic energy as well as the potential energy of this theory, and therefore they persist to be true eigenstates of this theory at any finite lambda. Okay. And so basically these directions are some things which I would call anomalous zero modes. And the punchline is, if you take any initial state which has a strong overlap with these anomalous zero modes, that state would not thermalize. That state would show anomalous thermalization. Okay. So such anomalous zero modes would violate this paradigmatic eigenstate thermalization hypothesis. And these are also sometimes called quantum many-body scars in the literature. And maybe many of you may have heard this term already, and this was introduced in this reasonably influential paper by Turner and collaborators. Okay, good. So now, what do I mean by this memory effect and thermalization, right? So here comes the point. So here, I'm just showing some exact diagonalization data for a quantum link model defined on a ladder system with, so if you remember, just to go back here, so this is my ladder. So imagine this is Lx and this is Ly. And I forgot to mention that I take periodic boundary conditions in both directions for both this problem as well as for the quantum dynamo problem. Okay, so I just take this ladder system, and in this ladder system, let's say I fix Lx to be 14 and Ly is 2. And as is well known, these link models and dynamo models can also be thought of as spin half problems with the constrained Hilbert space. So basically, if you do this counting, there are 56 spins here. Okay, so then you start with some particular states, some particular initial states, which are completely unentangled initial states. So basically, these initial states are, if you wish, diagonal in my SZ basis. So they are completely unentangled. And I want those initial states to have the same energy density, right? Because I want to see how these things thermalize. And of course, in a unitary evolution, this energy density is a conserved quantity, right? So here I choose the energy density to be lambda times n plaquette by 2, np by 2. So this np is just the total number of plaquettes, elementary plaquettes on this lattice, okay? So it turns out that there are 6,433 initial states with exactly this energy. If you just do a scan of all your Fox states, okay? 18 of these initial states have a strong overlap with these anomalous zero modes, okay, which I'll of course elaborate on during my talk, whereas the rest of them do not have a strong overlap with these anomalous zero modes. So in particular, consider two such initial states which do not have a strong overlap. Now see, this is the classic signature of thermalization, even though, okay, so there is some local correlation function I measure here. There's some flux correlator or some SZ correlator in the spin language. The detail of what it is not so important. It's just some local correlation function. So you see, I take two initial states with this energy density. In the initial states, this correlation is very, very different, as you can see, at low times. But as time progresses in this unitary evolution, you can see that these local correlations approach each other. That's the classic notion of thermalization. So you can already see what I mean by self-thermalization in a strongly interacting quantum theory. But these 18 states, which have strong overlap with these anomalous zero modes, in particular, have just drawn one such initial states. These guys don't thermalize, as you can clearly see here. So that's this memory effect in this unitary dynamics, and this is what I call anomalous thermalization here. Okay. So this is rather non-obvious because this is a strongly interacting theory, right? So you wouldn't have guessed this. And just to give some numbers, so I have done this, so this calculation was done using exact diagonalization. So of course, there's a constrained Hilbert space. So the number of states here is lower than, 2 raised to the power 56. So if you implement this Gauss's law of 2 in, 2 out, the number of states is this. Then I project onto the zero winding numbers. This concept of winding number was also introduced by Srijit in the previous talk. So the winding number is a topological invariant here. So local dynamics cannot change it. So I just start with the largest winding number sector, which is 0, 0. That reduces the number of states to this. And then, as is often done in ED, you can use conservation laws to further simplify your life, right? And then you get some manageable numbers and you can do these calculations, right? Good. Okay. So now let's go on and try to demystify all this. So let's first focus on the mother point where the index theorem is true. So I go to lambda equal to 0. At lambda equal to 0 in the computational basis of SZ, this is a purely off-diagonal matrix for the Hamiltonian, right? So, so the crucial feature is that at lambda equal to 0, the Hamiltonian commutes with a certain chirality operator. And I have just tried to indicate this chirality operator pictorially for the quantum link model here. So you can, so this chirality operator is the product of all the fluxes along these pink lines, okay? Right, along all these pink lines or along the spins which live on the centers of these lines, right? Because this equivalent spin half problem can be thought to live on the dual lattice of this particular parent lattice, right? So it's some product of lots of fluxes or a product of lots of SZ operators, right? Which are all +1s and -1. So this whole thing can either be +1 or -1, okay? Good. So now the key point is each plaquette here contains only one such pink line, okay? From this, you can easily prove that, and using the sort of algebra of Pauli matrices, you can easily prove that at lambda equal to 0, the Hamiltonian anti-commutes with this chirality operator. Because it does so, if you take a many-body eigenstate of such a theory, which I denote by E, if you hit it with this chirality operator, it gives to you a many-body eigenstate of this theory with exactly the opposite energy, -E, okay, because of this anti-commutation. Good. That immediately implies that at lambda equal to 0, the spectrum has a E to -E symmetry, which is exact. Therefore, zero modes mean something, right? So E equal to 0 is special. You cannot rescale the Hamiltonian and change 0 to something else. So yeah. The second important thing is that this Hamiltonian commutes with certain spatial reflection symmetries here, okay? So there are these point group symmetries along these reflection axes which commute with the Hamiltonian. And not only that, these reflections also commute with the chirality operator, which can be checked, okay? Now, if these three things happen together, then it turns out that there is a very nice index theorem, which was recently realized in the community, which ensures anomalously large number of zero modes in the spectrum. Okay, as you can show from the ED, as you can easily see from the ED data. This ED data on ladders for the quantum link model, and you can clearly see this sort of huge number of zero modes jutting out here, right? So in fact, in the thermodynamic limit, the density of states would have this form, right? So this is a regular function, and there is a delta function riding, Dirac delta function riding on top of it, okay? That basically signifies the macroscopic number of zero modes here. Good. So let me try to just quickly demystify this, how this thing arises exactly at lambda equal to 0. So, just for illustration, I'm taking some pictures from some slightly different contexts in some slightly different model, but those details are not important. So the crucial aspect to realize is that basically, if you think of this Fock space, you can think of the action of the Hamiltonian in Fock space in terms of a graph. So let's say you start with some Fock state, you hit the Hamiltonian on that Fock state, let's say like this, then that Hamiltonian may connect it to some different Fock states, right? Then you keep hitting it like that, and it generates some very complicated tree, right? Structure or a graph structure in Fock space, right? Now it turns out that this graph structure has a crucial property at lambda equal to 0. There is an emergent bipartite hopping structure here. Okay, so what I mean by that is this chirality operator. So in this sort of slightly different problem, the chirality operator is just the product of these sigma z's. So if something is black here, it's just sigma z equal to +1. If something is white, it's sigma z equal to -1. So this guy, for example, has c equal to -1, right? Because it has 3 -1s, right? The c equal to -1 is only connected to c equal to +1, as you can see. The c equal to +1 is only connected to c equal to -1, as you can see here, right? So there's a emergent bipartite hopping structure in Fock space. And this is due to this relation, okay? Now let's say I switch over from this many body problem in Fock space to a one body hopping problem. Now, in a one body hopping problem, it's well known that if you have a bipartite lattice where there is an imbalance between the number of points in sublattice A and the number of points in sublattice B, maybe you can just say that c equal to +1 is sublattice A and c equal to -1 is sublattice B. Then just from linear algebra, you can show that for such a problem, the number of zero modes is bounded above by the difference in the two sublattices or the sublattice imbalance. Okay, and there have been many nice works on this, and I in particular point you to this nice paper by Sutherland for some interesting physics that comes out of it. But this is a many body problem. So crucially what happens here is, and I see that I'm already doing bad on time, crucially what happens here is that as I already indicated to you, this chirality operator commutes with this reflection symmetry. You can think of this reflection symmetry like some kind of a parity operator, because if you hit it twice, you just go to the same state, right? And this reflection symmetry also commutes with the Hamiltonian. So basically what that means is that this bipartite hopping structure is also preserved if you go into the into a block diagonal into a block which has a well-defined parity, and this parity is given by this reflection operator, right? And using a combination of this, now you can actually show, and maybe I'll skip over this. Yeah, okay. You can actually show that you can use exactly this formalism which was introduced by Sutherland, and you can show that the number of zero modes in this many body problem or in this hugely complicated graph which lives in Fock space is actually bounded by this number n. So this is basically what I'm saying is that the number of zero modes has to exceed this number n, where this number n increases exponentially. So if the total Hilbert space dimension of your full problem goes as alpha to the power v, where v is the number of lattice points in your theory, then this n can be shown to scale as alpha raised to the v by 2. So this is a macroscopically large number of zero modes. Okay, right. So now, because your theory has a E2 minus E symmetry, these zero modes actually should resemble infinite temperature states, right? Because they are exact mid-spectrum states. So from eigenstate thermalization hypothesis, a typical zero mode should resemble a featureless infinite temperature state. Okay, but it turns out that these anomalous zero modes are very peculiar. So why are they peculiar? So let me just give you a very short derivation of why they are peculiar and must violate the eigenstate thermalization hypothesis. So you see, as I said already, these anomalous zero modes are simultaneous eigenvectors of O kinetic and O potential. So because it's a zero mode, O kinetic hitting on this anomalous zero mode is obviously zero. Whereas O potential hitting on the zero mode gives you an integer times the same state, because O potential is just a counting operator, so it can only give an integer as a eigenvalue, right? So basically, if I tune lambda, then these states, which I have indicated by blue here, stay unchanged, whereas all the other many body eigenstates which are in the neighborhood of these states, they of course completely change, because there's an exponentially small gap at high energies, so any perturbation is a large perturbation. So that obviously shows you that because these states are unchanged, they cannot be typical states, and there are consequences of this. First consequence, they violate eigenstate thermalization hypothesis. Second consequence is, if you think of these states in this graph, these states, these anomalous zero modes are highly localized, whereas everything else is highly delocalized. Okay, the typical zero modes are highly delocalized. So here I just show some numerical instance of that. So I measure something called the half-chain entanglement entropy of these things at some non-zero lambda. In particular, I tune to the RK point. Okay, and you can see that there are these anomalous zero modes here, which actually sort of have a much lower entanglement entropy than anything else. And the reason is that they violate ETH, okay? And these modes are exactly the modes which sort of gave rise to those anomalous thermalization in the 18 initial states that I had indicated previously. So I'm sorry, I'll just rush a bit to drive home a main point now. So because I see that I don't have much time left. So you can of course raise the question whether such anomalous zero modes
You
are.
have like 15 minutes.
Oh, I see. Including
Slightly
questions?
short. Hmm?
Including
Well,
questions?
not really.
Okay, so okay, thank you. Yeah, okay. So then let me elaborate. Okay, so these anomalous zero modes, if you just sort of decompose them into the zero modes from your exact diagonalization at lambda equal to 0, then of course they look like some very pseudo-random superposition of these zero modes, right? So the idea is that lambda equal to 0, the anomalous zero modes are of course many body eigenstates of your theory, but at lambda equal to 0, any zero mode is also an eigenstate of your theory, so there's no pinning in your theory. Whereas the moment you turn on lambda and you break the index theorem, these anomalous zero modes become pinned, because they are the only eigenstates which are left from the zero mode spectrum, and the rest of the zero modes mix with the non-zero modes. So that's why it's like an order by disorder mechanism in the Hilbert space. And the consequences are, you see these weird thermalization properties in these many body interacting systems. Now you might ask, okay, I have shown you some exact diagonalization results. How do I know that these kinds of phenomena persist in the thermodynamic limit? Well, I can answer this question by just presenting a case where I can solve for these anomalous zero modes in the infinite size limit, right? And at least that should convince you that this is not some finite size effect. So to do that, let me construct these some things which I call exact Lego scars, but now in the quantum dynamo model in the thin torus limit. So what do I mean by that? So I take a ladder now, and the width of the ladder I fix to Ly equal to 4, and the length can be arbitrary. Okay, and there are periodic boundary conditions in both directions. That's why it's like a torus. So basically what I'll show you is that a class of these anomalous zero modes for the quantum dimer model with just the RK Hamiltonian can be written like this. So it's a game now. There are all these Legos, and you can sort of fit these Legos together as long as there are certain things which, so the Legos have some interior, which are entangled structures, and the Legos have some exterior, which are some sort of bits, and these bits have to smoothly sort of connect together. And so that's why it's like a Lego game. As long as you can play this game with the correct Legos, you can build a structure like this, no matter how large this LX is. Okay. And these Lego scars can be interpreted to be states which have excitations that exhibit subdimensional motion. And in fact, they have some strong connections to fractonic theories, but I won't have the time to go into that now. In fact, what you can further show is because these Legos come in multiple varieties. So then if you take a long torus, because there are lots of these kinds of Legos, you can easily show that there is an exponential LX number of these Lego stars when LX becomes large, which are all anomalous fields. Okay, good. So let me just illustrate this idea. Okay, so in particular, let me just show some result first on lattice. Now I've switched my orientation, which has Ly equal to 4 and Lx equal to 6. Now, let's say numerically I discover a particular Lego scar using my EB. Now this Lego scar, if I write in my Fock basis, has an extremely simple representation. Even though it's a high energy state, and for normal high energy states, you expect that if you write them in your Fock basis, you should have a huge number of Fock states which contribute to this state. Here you see only 4 contributing Fock states. Okay, and they have a very particular sign structure, as you can see. Now you can easily represent the sign structure and the state by the notion of emergent singlets, which I have tried to show here. So there is this Lego here, which I call L1, which has this emergent singlet where this guy is anti-clockwise and this guy is clockwise, and vice versa. Okay, and these two guys are not flippable, and something. And this is the other piece of the Lego, right? So you can actually show that this Lego can be fitted to this Lego, this one, because you see I have not drawn it here, so the arrows here go like this, the other way. So you cannot put this Lego on top of that Lego, but you can put this Lego on top of that Lego. That is what I meant by connections at the boundaries of the Lego. Okay, so you can fit L1 to L2 to give you a legitimate state. And in fact, you discover the state in EB. Now, suppose you fit L1 to L2 and again fit L1 to L2, then you get such an anomalous zero mode for Ly equal to 4, but Lx equal to 6 times 2, which is 12. And you can just keep playing this game, right? So you see what's happening here. Good. So now, you see, there's this very interesting notion of an active zone here and an inactive zone. So basically, it seems that the excitations are only flowing this way, and they're not flowing that way here. So you can ask why on earth that's happening. That's happening due to this particular sign structure here. So basically, you can easily show that because of the sign structure, certain excitations here. So this U means unflippable, this C means clockwise flippable, this A means clockwise, anti-clockwise flippable. So if you add this O-kinetic operator on such a structure, it actually generates something like anti-clockwise, clockwise, anti-clockwise, clockwise structure. Where if you add the Hamiltonian again, the excitations actually leak upward and downward. But because of the sign structure, you see this guy exactly cancels this guy, and that's why there is this subdimensional motion. Okay, so this is an emergent property due to the sign structure inside the leg. And so that's where this emergent fractonic physics comes in. Now you can keep playing this game and you get lots of fun things. You can get fatter Legos here with bigger inactive zones like this, and you can create these structures. You get still fatter Legos here. I'm just showing one of them where you see, not only do you have these emergent singlets, you have some emergent object with 4 degrees of freedom. I don't know what to call this, but this is sort of the wave function of this. This is clearly not a singlet. And so you can just keep playing this game, right? And you play this game and you just build this zero mode even in the thermodynamic game, right? So there's an incredible variety of these zero modes, which I haven't touched upon this talk. I have just touched upon something called type 1 states here, but I haven't touched upon many other things due to lack of time. But I think this might be a good point to conclude. So basically, even though I have talked about two very particular models here, the quantum dynamo model and the quantum link model, what I'm trying to indicate here is something more general. So there may be a class of theories, right? And in fact, there are very well-known lattice gauge theories and condensed matter systems, which in their parameter space, extended parameter space, harbor strongly interacting points. So these points don't have any weak coupling description. And these strongly interacting points have null spaces protected by this index theorem. And then you can add certain perturbations. In fact, this word perturbation is also a misnomer because this lambda can be order 1, as I already showed to you during my lecture. These perturbations actually stabilize certain very interesting anomalous states, which have overlap with simple initial conditions, and those simple initial conditions do not thermalize. And at the moment, we are thinking about how to extend this mechanism to non-abelian lattice gauge theories and also fermionic models. Okay, so I thank you for your attention, and yeah, thanks.
For the next talk. So questions from the audience. People seem to be hungry. Okay, maybe I have a question. I mean, the lambda equals 0 is just the point where you have only the hopping.
Yeah.
Yes, right.
Kinetic term. Yeah.
Right. So, and you showed those zero energy states at the end. And if you add, and maybe I didn't listen carefully, if you add the potential energy, I mean, you can add different type of potential energies. I mean,
Right.
either the Becca like what you did, or maybe very differently the vertices.
Yeah.
These will still remain exact eigenstate, even if you add the, I mean, they can modify somehow. I mean, you show that there's 0.505 amplitudes. Do they still remain exact eigenstate?
I see what you mean. Yeah, so the Lego scars that I showed, they are exact eigenstates only when the potential energies of the Rokshar-Kivelson form. Okay. Now you can of course add some other potential energy, right, which is different from the Rokshar-Kivelson Hamiltonian. In that case, what is going to happen is the following. So let me sort of clarify this a bit. So you see, at this lambda equal to 0 point, there are lots of anomalous states. Okay, there are lots of anomalous zeros. Certain potential energies stabilize certain directions, while other potential energy terms stabilize some other direction. So I hope I have answered your question. So if you add some potential energy term, which is, let's say, not the sum of okay, so just to illustrate, so let's go to this potential energy. Sorry. Yeah, so let's go to this potential energy. Let's say I put a staggering term here. If something is clockwise, I put a 1 here. If something is anti-clockwise, I put a -1 here. So that's a different potential energy, right? With this different potential energy, you can actually stabilize some other quantum scars. Okay. Yeah, so that's the point. So it provides a different pinning term, right? Yeah.
Yes, thank you. Yes. Audience, yeah, please.
Arnab, nice talk. You spoke about link model mostly.
Yeah. Well, I did also speak about the quantum dynamo model because the Lego scars are in the quantum dynamo model. You see, this thing, Bhaskar.
Okay, I missed that.
Oh, yeah.
So you have zero.
This thing. So you see, this thing we could only construct for the quantum dynamo model.
Okay. And you have macroscopic number of zero
modes. Exactly. For the quantum link model, we can numerically establish this, but still I don't have an analytic construction of these anomalous zero modes, right? Yeah.
So another short question is, the eta particles in Hubbard model, for example, in 1D Hubbard model, they are zero energy eigenstates of kinetic energy alone. So do they possess similar properties when you look at this?
Well, that's an interesting question. They might, because I have also been thinking of other problems here. So I don't know the exact answer to your question, but I think this is a very general thing. I think whenever you can show that there is this index theorem here, and then you perturb it Now the question is, what are the right perturbations? That's really the question which we are trying to think about now, right? So if you perturb them correctly, then you'll always generate these anomalous states, right? So,
thank you.
Yeah.
Any further question? Maybe I ask one more question. So you show that this is ultimately connected with the bipartite nature of your hopping, like
the index
Hamiltonian.
theorem. The index theorem.
Yes. Now, and you mentioned that maybe I misunderstood that it depends on the actual basis you work in. Or maybe not.
No, it doesn't, because of course, whether some theory has a macroscopic number of zero modes or not is a basis independent statement. Right. So
Yes.
Carlos, just to elaborate on this point, please note that only at lambda equal to 0 is the index theorem valid. The moment you go to non-zero lambda, the index theorem is lost. The reason it's lost is that the chirality operator that I defined no longer anti-commutes with your Hamiltonian. Okay. So in that sense, it's really like order by disorder in the Hilbert space, right? So there's an exponentially large number of zero modes, right, at lambda equal to 0, which are protected by some index theorem. Now you turn on some coupling, and that breaks the index theorem. Of course, you would then assume that, you know, this huge exponential degeneracy is lost. Indeed, it is lost, but there are some special directions which really get stabilized as, you know, eigenstates of this full theory at non-zero lambda, and that those new directions, because they are simultaneous eigenvectors of the potential energy and the kinetic energy of your theory, must violate eigenstate thermalization hypothesis. So they must be anomalous. Yeah.
Okay, thank you. I think if there are no more questions, so let's thank Arnab again for this nice talk.
Thank you.